Today's lesson is 6.3, Apply Properties of Chords. So let's go ahead and review the definition of a chord. A chord is a line segment inside the circle that connects 2 points on the circle, but never the center. So here is an example of a chord. There we go. From one side to the other, you could go ahead and call this point A and this point B, and then we can start talking about that chord. Today we're going to talk about 4 different chord theorems, and we're going to see how to apply them in situations today. So here is our first theorem. In a circle or in congruent circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent. So what this theorem is saying is that arc AB is equal to arc CD. That's this part right here. They are congruent if and only if AB, my chord, is congruent to CD, my other chord. Okay? Only if the chords are congruent are the arcs congruent as well. So let me go ahead and highlight those arcs for you that they're talking about. So these 2 arcs are congruent if my chords are congruent. Let's go ahead and take a look at an example of this. Remember, you do get a lot of information from reading the sentence that is above the diagram, but you do get a lot of information just by looking at the picture. The sentence is saying that circle P is congruent to circle Q. And chords F, G, and J, K are also congruent. So I know that these 2 circles are congruent. I can see that because they both have a radius of 5, and that makes them congruent. But I also am reading that this chord and that chord are congruent as well. So I can go ahead and I can mark that in my picture. Okay? We saw right above in the last theorem that if the chords are congruent, then their corresponding arcs are congruent. So if this arc right here is 80 degrees, then guess what? So is this arc right here. So my answer to the measure of arc FG is simply 80 degrees. All right, let's take a look at another example. I have 2 congruent circles, M and N. They want me to find the measure of OP. They want me to find the measure of OP. Now, it's not so obvious that these 2 are congruent circles. I can see that one is marking the diameter and one is marking the radius. But remember, the diameter is just half of the radius. The radius is just half of the diameter, and 10 divided by 2 is 5. So these 2 both have a radius of 5, which makes them congruent circles. Plus, we were told right here. They want me to find the measure of this. Well, if these are congruent circles, then this chord is congruent to this chord. So if EF is 60, then so is OP. All right, let's take a look at our next theorem. If one chord is a perpendicular bisector, let's go back and remind ourselves what perpendicular means. So perpendicular means, this is my symbol for perpendicular, which means I have a 90-degree angle. And you can see that right here in your picture. You're going to have a 90-degree angle when you have perpendicular. Bisector, let me grab a different color. Bisector means we've cut in half. Cut in half. That's a bisector of another chord. So if one chord is a perpendicular bisector, notice we see our 90 degrees for perpendicular, and then we see our bisector by seeing that TP and RP are equal, then the first chord is a diameter. So take a look at our picture. If QS is a perpendicular bisector of TR, then that means that QS is a diameter of the circle. Okay, since we have our 90-degree right here, and we see that these two are congruent, that makes QS the diameter. All right, what we also know from this picture is, of course, that TP is congruent to RP. We know that as well from the bisector. All right, our third theorem for today is if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So this theorem is very similar to the other one. Let's go ahead and take a look at it. So we can see that EG is a diameter because it's going through the center of our circle. We can also see that EG is perpendicular to FD because it is marked with a 90 degrees. Therefore, HD and HF are congruent. Let's go ahead and mark that. They're being bisected. And it means that FG, the arc, FG, is congruent to the arc GD. So I can go ahead and say this arc is congruent to this arc. Okay, from F to G is the same as from G to D. All right, let's go ahead and take a look at an example of that. Let's take a look at our picture right here. And they want us to find the measures of two different arcs. Let's start with the measure of arc CD. Let's start with the measure of arc CD. I'm going to go ahead and just shade it in there. This is the first one that they want me to find. All right, so what I'm noticing from the last theorem is that I have a diameter because there is my center, and I have a perpendicular right here. The last theorem says then this and this are equal to each other, and that are equal to each other. So the last theorem says these two parts are equal, and it also says that these two parts are equal. There's what I'm going to do. Now I know exactly what to do. 9x is equal to 80 minus x. Okay, I can go ahead and I can solve this problem. If I need to, I can go ahead and drop my line through the center. It's not a bad idea. I'm going to move the like term over. 10x equals 80. Divide by 10. X is 8. I have to go back and I have to plug it in. So this is going to be 9 times 8, 72 degrees. There's my answer. Now part B is asking me to find arc EBC. Remember when you have 3 letters to name your arc, you just follow them in order. So from E to B to C. E to B to C. So this is 72. This is also 72. But I could come in here and say 80 minus 8 and do the 72. But I already know that they are equal, so they both have to be 72. So I'm going to say 72 plus 72, 144. Okay, but that only gets me here. They're asking me for this. EBC is this. EBC is this. I remember. The total of my circle is going to be 360 degrees. So if I already know that this part is 144, all I have to do is subtract. So I'm going to go ahead and say 360 minus 144. And that's it. That's my answer. So my answer here would be 216 degrees. All right, our final theorem for today says that in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant, the same distance from the center, equidistant, the same distance, equally away from the center. So what this theorem is saying that when my picture looks like this, AB and CD are congruent if and only if this little guy is equal to this little guy right here. So only if FE is congruent to GE. Now, some things have to happen to ensure that they are congruent. See these little 90 degrees? They've got to be there to lock E in place and make these two pieces between F and E and G and E to be congruent. When that happens, then we also know that this arc and this arc are equal. We also know from the previous ones that this chord and this chord are congruent, and then this arc and this arc are congruent. Now, this arc and that arc are totally different. These are totally different because they're not being locked into place. But from the arc from C to D and the arc from A to B are equal because the chords are equal. Okay, just to keep that in mind. Here is our final example. Chords QR and ST are congruent. So not only am I telling you in the sentence, but I'm also showing you in the picture by saying that they're both 16. Now, I didn't have to do both of those, okay? But I did. They are equidistant from the center. They are equidistant from the center. So I'm giving you that fact that they are. I want you to go ahead and find X. Since they are equidistant from the center, that means that I know that I can say this and this are the same. If those are the same, I am simply going to say 5x minus 9 is equal to 2x. And I'm going to go ahead and solve this equation. Not a bad idea to draw that line through the equal sign, especially since I'm going to move the 5x this time because the 2x is already by itself. Okay? 2 minus 5 would give me negative 3x. I'm going to divide by negative 3. I know, I bet you guys were thinking, oh, miss, no. But x equals 3, and there's my final answer.